Hello, and welcome to the ARSET training, Crop Mapping Using Synthetic Aperture Radar and Optical Remote Sensing. My name is Sean, and I'm an ARSET trainer based at NASA's Goddard Space Flight Center in Greenbelt, Maryland. It's a pleasure to welcome you all to the first part of this three-part webinar series. For those unfamiliar with the Applied Remote Sensing Training Program, or ARSET, ARSET is part of NASA's Applied Sciences Capacity Building Program. ARSET provides accessible, relevant, and cost-free training on remote sensing satellites, sensors, methods, tools, and applications. Trainings are offered online and in person for beginners and advanced practitioners alike. Trainings cover a range of datasets and analysis tools and their applications to water resources management, air quality, disasters, land, climate, and energy. ARSET's goal is to increase the use of earth science remote sensing and model data in decision-making through training for professionals in the public and private sector, environmental managers, as well as policymakers. Trainings are freely available to anyone with an internet connection and conducted either live, instructor-led, or self-guided, such as our Fundamentals to Remote Sensing training. Since 2009, the program has reached over 50,000 participants from over 170 countries. All ARSET materials are freely available to use and adapt for your curriculum. If you use the methods and data presented in ARSET trainings, please acknowledge the NASA Applied Remote Sensing Training Program. Over these 2 weeks, there will be 3 2.5-hour sessions, which will include presentations, demonstrations, as well as question and answer sessions. The same content will be presented at 2 different times each day. Session A will be presented in English, and Session B will be presented in Spanish. All materials and recordings from each session will be available from the training webpage provided by the link on this slide. There will be one homework assignment for all 3 parts of the training. Answers must be submitted via Google Form, which can be accessed from the training page on the ARSET website. Homework will be made available on April 11th, with a due date of April 25th. A certificate of completion will be awarded to those who attend all live webinars and complete the homework assignment by the deadline. You will receive a certificate approximately 2 months after the completion of the course from Marino Martin. The prerequisites for this 3-part training are the Fundamentals of Remote Sensing Session 1, Agricultural Crop Classification with Synthetic Aperture Radar and Optical Remote Sensing Part 1, as well as the Mapping Crops and Their Biophysical Characteristics with Polarimetric SAR and Optical Remote Sensing. Links to each of these trainings are provided, and we encourage you to go through them to familiarize yourselves with content directly related to this training. This slide outlines what each part of the 3-part training will cover from April 4th through April 11th. We hope you will join us for all 3 parts to gain as much value from the training as possible. If you are not able to attend one part, a recording will be made available within 48 hours of the training day on the ARSET website. After participating in this 3-part training, attendees will be able to explain how polarimetric parameters are used for crop condition assessment, demonstrate how to perform Sentinel-1 SAR preprocessing to derive quasi-polarimetric parameters, perform a calibration of a SAR-based vegetation index to NDVI, monitor crop growth with multi-temporal polarimetric SAR or PoISAR data from Sentinel-1, examine crop growth using a canopy structure dynamic model and time series of Sentinel-1 imagery, and classify crop type using a time series of radar and optical imagery, both Sentinel-1 and Sentinel-2. It is now my pleasure to introduce the guest trainer for today's webinar, Dr. Armando Marino. Dr. Armando Marino received his Master's in Science in Telecommunication Engineering from the Università de Napoli Federico II in Italy, and his PhD in Polarimetric SAR Interferometry from the University of Edinburgh in the UK. He has worked in several European institutions, including the German Aerospace Center, the University of Alicante in Spain, ETH Zurich in Switzerland, and the Open University in the UK. Since 2018, he has been a senior lecturer at the University of Stirling in Scotland, UK. His research interest is in processing of synthetic aperture radar images, with special interest in polarimetric and multitemporal datasets. He has worked on several applications in the marine and land domains and has developed ground-based radars for validation of satellite data. Armando, over to you.
Hello everybody, I'm Armando Marino from the University of Stirling, and thanks Shane for the introduction. Today I would like to present you this training on crop classification using time series of polarimetric SAR data, and by the use of Python and a Jupyter notebook. So as you heard from Shane, my interests are about processing of polarimetric SAR data, in particular using time series. So doing works similar to what you will see today, with different type of application, going from maritime to terrestrial applications. But now let's start with the presentation now. The learning outcome for this for today are listed here. You can see at the end of today you will be able to run a machine learning approach for multitemporal polarimetric data using Python. You will see how to pre-process your polarimetric SAR data in order to be able to use into machine learning applications. You will see how to format your feature vectors, which will be the input of these machine learning algorithms. And you will see probably that this is one of the most complicated bit to do when you work with machine learning. Now they have libraries for everything, but we still need to format the data in a way that is useful for us to use them. Then we will run two types of classifiers. One, the random forest, is a supervised one. The other, the k-means, is an unsupervised one. And at the end, I will tell you how to evaluate accuracies for these classifiers. And this is really a very important point. It is really essential that when you produce these maps, you try to assess the accuracy of your maps. Before we start, I would like to let you know that this is a continuation of a previous training that we did with ARSET. It was called Mapping Crops and Their Biophysical Characteristics with Polarimetric SAR and Optical Remote Sensing. And you find the link here. You will see what we are doing here, build up on the skills that you would have learned inside this initial practical. So unless you are very familiar with Python, my suggestion will be that you look at this training and go through this training before you start this one. Otherwise, you see some bits may get a little bit complex. So you should have received a folder where you will find the data that we will be using for this practical. You will see there are several files there. There is a document, a Word document that tells you how to install Python and how to install libraries. And the data are there for you to use. And there is also some files that we will use in our Jupyter notebook training. You'll see there are several versions, but I can tell you more about these different files in the next slides. So Python, I don't think I need to talk more about Python. It's now one of the most famous programming languages at the moment. The good things of Python is that it's quite general purpose, so allow you to do really different things, not just processing the data or do statistical analysis, but really you can do many things with it. If you're not familiar with Python, don't get too scared. The tutorial now is explained step by step. But if you want to know more, then my suggestion is for you to do this tutorial here. Is the official Python tutorial. It is quite long, but after that you really get a good grasp of what Python can do for you. And to install Python, my suggestion is that you use Anaconda. So by following this link here. Anaconda provides you with this installer for the Python, for the editor, and also a lot of libraries that comes with it. And all the libraries we will be using today are inside the Anaconda installer. So if you manage to install this, you don't need to install any further library for this training. And so once you go to the website, you have to choose your operating system. Be very careful to choose a 3-point-something version. Probably 3.8, 3.9 will be very good. The 2.7 version is the old one, and the code that you're using today will not run with a 2.7 version. So if you use 2.7, you will not be able to run the training today. So once you have installed, if you have Windows, you will see that you will find inside the Start menu, you will find the information about the Anaconda installer, what we have installed. And what we will be using today is this one, Jupyter Notebooks. You will find a button there. You just click on it and you will start. I will show you how to do later. Once you click on that button, so once you start your Jupyter Notebook, a browser will open. So this is inside the browser that you are using. It's a default browser. And you will see a list of several folders here, which are your Jupyter Notebook folders. In order to create a new folder, you can go here, new, and you say new folder. If you want to run the scripts that I have given you for this training, you will need to upload them to the folder that you have created. You see here I have a folder ARSET 2023. You can call it as you want. You go inside there and upload the files on that folder. Also, I want to point your attention to this other editor called Spider, which will come with Anaconda installer as well. And Spider is one of the editors that you can use. There are many others. Spider, I quite like it. It's quite easy to use. Also, if you are a user of things like MATLAB, you will see or R, you will see is very, very similar to things like RStudio or MATLAB. But anyway, this allows you to run the code without opening a browser and without you clicking all the times that you want to run a cell. So if you want to automate your processing chain, that is my suggestion, is that you use an editor like Spider. A few words about the dataset that we will be seeing today. So this is Sentinel-1 data, SAR satellite from the European Space Agency in C-band. And it is dual pole, so you have two polarization channels there. The location of interest is in Scotland, this area here, which is a shire called Angus, near the city of Dundee, which is this place here. So here I have a land cover map of the area, although the crop area is not classified in different type of crops, it's just agriculture crop. And there are several classes here. There is the city here, marshes, and these are the tidal areas, because the tides here are quite large, so 6 meters you can get. This is how this area look with the Sentinel-1 data. So this is an RGB obtained using the two polarizations. I will tell you more how to obtain this image later, and was taken in 2019. And this is the city of Dundee, and the area that you can see from the map before is represented here. During this practical, we will focus on a small area of all the dataset. This is to allow you to run on machines that may be not very powerful or very fast. So we just concentrate on a 500 by 500 snippet, little image, little part of the image inside your dataset that I'm sharing with you. And here you can see the agricultural fields are this part here. The urban area is represented here. This is actually a town more than Dundee. Is that the town on the side of Dundee? And this is pasture and marshes. And the sea area is down here. We are now ready to start our tutorial. first things you will need to do is to start your Jupyter Notebook application. In Windows, you will find in the Start menu, and you just click on it. You'll see there is a terminal here opening where the software is started, and there will be a link here inside your browser. Close this too so that we have more space to see this one. These are the folders that I have inside my notebook. You will not have these two as a default inside yours, but you can add a new folder by going here, new, and then folder, and write the name. And once you are ready, you created that, you can do an upload, which will lead you to then browse your files and get those files uploaded inside your notebook. So at the end, your notebook should look something like that. Maybe you will not have this folder called here, but it will look similar. So we start with this file here, PoISAR time series. Once you click on it, then you should start looking at the script. So in this first file here, what we do with this first script, we apply machine learning to PoISAR time series using Python. And the idea here is to format the data in a way that we can more easily use in a machine learning approach. So we are producing the elements that we will be using inside our feature vectors in the next part of the training. As I said before, we are using Sentinel-1 imagery, which are from the European Space Agency. They were acquired in 2019. And here I'm sharing 19 images with you in this area in Angus, in Scotland, near Dundee. If you go to Copernicus, so you go to the Alaskan satellite facility, you will see there are many more images over the area. And this is a quite well covered area actually from Sentinel-1. I didn't provide, I'm not providing you with original data because they are way too big to share. So there will be many, many gigabytes, which is not possible to share in this training. So what I'm giving to you is just a small area where we can run this training. But once you feel confident that you can run this code properly, my suggestion is that you go to the Copernicus or the Alaskan satellite facility and you get the data yourself and you do all the passages so that you make sure you can apply this not just in Angus, but anywhere you want around the world, landmass of the world where Sentinel-1 images are available. Few words about what I did to this data before creating formatting, as you will find. So what I did is to calibrate the data. I applied orbit files. I made a subset, then produced the covariance matrix, multi-looked 4:1 to make the pixel more square on the ground, co-registered, stacked, and geocoded the images. So what you get are geocoded and co-registered images. The format that Snap, I forgot to say, I used Snap for this. In particular, I used the GPT, the graphical processing tool of Snap, which you can call directly from Python. So it's all automatic after you install Snap. So it's all, you can do it automatically straight from Python. So the images comes out of Snap in a binary MV format. So they are binary file with an header. And to read them, you can use any GIS software, all will do. But the good things there, so they're relatively easy to read also with Python because they are binary. So you don't need really special libraries to be able to do that. So the area again is this one, and this is the land classification map I was showing before. But let's start with the actual practical. First of all, I would like to tell very few words about how to run a Jupyter Notebook script. So when you click over a place in the Jupyter Notebook, the things will highlight. This bit here is called a cell. This cell in particular is a markdown. You see, you can select between markdown, code, and other things like headings. And if you want to modify, to edit the content here, you have to double click. Once you double click, you see the editing function comes into play, and these things looks a little bit like LaTeX if you're into that. So you can like sort of writing in LaTeX, it's not exactly the same, but you can sort of use this kind of things to write your markdown. Once you are happy with what you wrote, you can run the cell either by clicking run or by the shortcut Control Enter in Windows or Shift Return in Mac. Once you have run, you see it goes outside from the editing view. If you want to have a new cell, so then you go to the side here so that you are in view mode and not editing mode, and you press the button B. Click the button B. This creates a cell below. If you want to remove a cell, you go again on the side here to highlight the cell, but not editing, and you press double D, twice the D key. So D, and it disappears. And this is possibly everything you need to know in order to run this code. Another thing says that if you in the code you see an hash, it means that is a comment. Comments like markdowns are written for humans and not for machine. When the machine see the markdown or see the hash, it just goes through, doesn't run it. It's just text messages for humans that are having a look at the code. So we can now start, and I'll briefly introduce the different parts of this initial script that you will need to run in order then to run the second script, which is the core of the training today. So at the start, we always import all our libraries here. And then we have a bit where we define functions. This first set of functions are for changing the name convention of file that come from Snap. So the file name convention coming from Snap is not the easiest to use to do what I'm doing here. You may want to change the file names. You can do it manually and spend half a day with that, or you can write some code with Python and let the machine update the file names. So the convention for numbers and get the dates from the stack. Next function is about reading a single MV image. Remember, the images coming out of Snap are in binary MV format, so we need to read them. And if you manage to install this library called Spectral, where we call the function MV here, I can show you the things before. So if you manage to install this library here, then you can use it straight away, and you are able to make your code more robust without avoiding hard coding. But if you don't manage to install this library Spectral, then you will be stuck. So to avoid that, what I did, I coded a way around it where you basically use the same, only the libraries that come straight away from Anaconda. You don't have to install extra libraries. I will tell you more about this when it comes to the hard coding bit, but it's not good to hard code. So if you manage to install Spectral, your code will be better. So anyway, this reads a single image. This function here reads a set of polarimetric acquisition, a set of images. In the dual pol case, we have two images as input, which is the HH and VV. But after we add VV, VH, depending which type of dual pol the satellite is acquiring. But once we run the Snap script, we will have data formatted as covariance matrices. These are 2x2 matrices where you have 3 independent images. 2 of them, the C11 and C22, are intensity of VV, intensity of VH, And the C12 is the cross correlation between the channel PV and VH. So they are complex. You have an imaginary, a real, and imaginary part. The difference with what we were doing before is that now we are using Sentinel-1, which is a dual polarimetric satellite, dual polarimetric modulus. So we have two channels. Next step is to have a function for running the Clopot-Tier dual polarimetric decomposition. This is because two of the Clopot-Tier parameters will be features for our machine learning methodology. In particular, we will be using the entropy and alpha. And here I need to stress something, that this is the dual polarimetric version of the Clopot-Tier decomposition. It's not the quad polarimetric one. So when you go doing this, besides having less outputs, so you don't have, for instance, the anisotropy, you don't have, for instance, the beta angle, but also the alpha angle that you get out from a dual polarimetric Clopot-Tier decomposition is not the same than the one you get from a quad polarimetric. So please don't use the same physical interpretation for this alpha angle than you were using for the quad polarimetric alpha angle. They are not the same. They are similar, but not the same. And the problem is that in dual pol, we cannot construct the Pauli basis. The Pauli basis is needed for that physical interpretation of alpha. If you do not have Pauli basis, then your alpha is ambiguous. You cannot really refer as you were doing before. Still very useful, just that the physical interpretation is not the same. So please be careful with that. Now, next step here is setting the file path where you have your data, so that you can process this data. Path is the folder containing the data that I'm sharing with you, so the 19 scenes. And you see the way I wrote it? Yes, double backslash is here. The double backslash is needed because if there is a slash and a number, Python misinterprets it as a symbol, so may make a symbol out of it. But if you put a double backslash, it knows and it doesn't do that mistake. So my suggestion is that you go to the folder where these things are, which in my case is this one. You go here, you do Control-C and then Control-V, you copy and paste inside the file, inside the script. And just a note about what you will find inside this folder. You see there is a lot of images here. You start with the C11 for the different dates. Then you go to the C12 imaginary, C12 real, C22 is just real, it's an intensity. And all the files have a header attached to it, these things here, which is a text file. So if you, this one, sorry. So if you click on it, you'll see it's a text file where all the information about your images are. Going back to the code. So, and also in this folder here, what you want to do is to have the folder where you are saving your outputs. These outputs are the ones that will be used in the second part of the training, the second script, where we actually run machine learning algorithms. So I hope you managed to do this copy and paste here, and this really should be the only bit that you will need to change in order to run this code. Then this part here is where we hard code the information about the image. Where do we get this information? From the header of the file. So you see samples and lines, these two numbers here, and these go here. And also this is the format. So it says that big endian, floating F4 is the type of format. If you use the library Spectral, you will not need to do this. The library is able to go in the header and read this information. But if you are not using that, then you need to hard code. So this bit here is extracting information about, so it's actually renaming the file names, so to have a different convention. The file names that comes out from Snap, they are a little bit longer, and they don't come alphabetical in terms of dates, which I don't like. I like to have them alphabetical order inside the folder. So I do this renaming here. This bit here is getting the list of dates inside the folder that you have. And one note of caution here. If you try to run this function and it's not working because you have a different operative system and the function I wrote is not appropriate, then you will get stuck. To avoid that, please uncomment these lines, which will give you the list date there, and then you will be able to run it after. The next part of the code, what you do is to prepare the cubes for processing. So as I mentioned before, we are only taking a small part of the data set. We are not using the full images. This is because you will struggle running on a computer which is not a supercomputer. If you have, say, a RAM of 80 gigabyte, 8 gigabyte or 60 gigabyte, you may struggle running the full image. So we take a block. This type of way of thinking of working with data is also called block processing. What we do here is the first step. We just select a block. We don't do for all the image. But if you want to run this over larger areas, then you will need to extend this, so to move this zoomed area to cover all your data of interest. And you will be doing something called block processing. Python is quite good in dealing with these things. Yes, some library they can do that. So this is way too advanced concepts for including here. The mantra here is to keep it simple. So I didn't include all these bits. But by any means, once you get to a certain level, you may need to use it. So in this part here, we select an area of interest. This is the area that I showed in the slide. So the little snippet 500 by 500 pixels. If you want to use all the area, that will be this part here. If you want to use a very small tile of the image just to see if the code is running properly, you can use this one. And with if clause, you can activate one of these by just uncommenting the line of interest. So now in this way, we are running area 1. If we want to run area 2, then we comment this and we uncomment this one. Now to do this trick that I just did to comment on uncomment a line was done by pressing Ctrl and then backshift. So I type it here, Ctrl plus this one. If you type this, if you press this one, then it will comment on or uncomment a line very quickly. So now we run, today we will run just this area here, but by any means try to change, locate in different areas and explore the data. Also see things that I'm not telling you, I'm skipping quite quickly on that, is that there are exercises here that you can do, things to make it more automatic, more robust. So once you're confident with this code that it runs properly, then try also this other way of processing to make it more efficient. Here you are ready to process the images. And before I start with this, what I'll do is can select everything is above this by just Control and arrow up. And then I can run everything pressing Control Enter. So let's go back to this point. So I press now Control Enter and just run everything above this cell here. So now we are in this cell here, and this cell does the processing image by image. It loads the dual polarimetric acquisition, does some filtering here, or take a little area in it, then does the filtering. and then runs the Potier dual polarimetric. So once you're here, Control Enter, and you see there is an asterisk here, which tells us that the machine is processing. You go at the bottom here, and they put let's say a countdown where we can see how the processing is proceeding. So now it's processing the first date, and there are 19 dates left. Now it's processing the second one, and so on. This will take some time, so I will go explaining the rest before this is finished. Sometimes you get these messages here, these warnings. Don't worry about them. It is okay. So there are places where there is some error calculating quantities. It's mostly in the Potier decomposition that happened that, but it's okay. Just a few pixels. The processing was not appropriate. There were errors there. There were problems, but it's not really a bug. It's keep on going. But once you have to program this to an operational level, then you will need to do it. Then you will need to make sure that there are no places where the algorithm doesn't work and give some spurious result. So you will need to make sure that the code is robust. But here we are just learning how to run it. So you can leave it for the moment. Keep it for another day. In this part of the code here, we want to visualize the images. And again, this is the area of interest with the different targets inside. And this is just a PNG. So if I click on this, you see just a link to a PNG. The actual image come out from these other lines here. So if you run this cell, then you will see the images coming out. And I'm not running this now because it's still running the part on top, but you will see the different images as here. And you see this, each one of these is for a different date, because I put a for loop here, which was going from date to date. The next part is about visualizing the Potier parameters. Again, a for loop to go from each for each date, and then here we bulk the images in a 2x2 format. So if you see what we have here, there are 4 images for each date. If you are interested in looking at the evolution of this feature in a smaller area, then you can proceed with the following code, where we select some region of interest. Now, to do this, there are several ways, and I will also tell you more about this later. Here we do the easy way by just selecting the pixels in the image that we want to look at. And then here we visualize these trends that should look something like this one. And the final part of this script is about saving these results into tubes that then will be loaded in the new in the second part of the training. The easiest way, the quickest way to save these images is by using NumPy arrays, which are again type of binary arrays, but proprietary of Python. And it is very easy because it's just a line of code for saving, which is save here, where you have to tell where our file, where we want to put this file. And then for reading, you will see it's a single line of code, it's called load. So it's very easy to do. That's why we are doing it. But you can, of course, save this in other formats. It is just up to you. I use this format just because it's the quickest way to do it. And this leads us to the end of this part here. If by any means you got stuck before, there was a bug in your code that you couldn't run, my suggestion is that you continue with the second part. If you're listening to me live, listen to what I'm gonna say in the second part, and then come back and try to do this using the recording. But let's now move to the second part of this training. So we can go back to our initial folder, Jupyter, and you will see the PoISAR time series we just worked with is highlighted in green, and so it's active, is running, as you see here. What you need to do is to shut it down so that it's not using resources anymore. So it's now off. You see, it's not highlighted anymore. It also allows you to close this window. We can close this one and now start with the second part, which should appear like that. But before I start with this, I would like to lead your attention to this other file here. Actually, what you do, I will show you it is easier than describing it. So you see there are two files. One is called PoISAR time series ML. The other is called PoISAR time series ML quiz. Now, if you're doing this live, so you're listening to me live, then my suggestion is just go to this one. You don't do the quiz. But if you're looking at the recording, then I would suggest you to go and try this one first. So if you go through this file, the quiz one, you will see that in some places inside the code, I substituted the actual code, the script, with the word quiz. If you try to run this, of course, you will crash because the word quiz doesn't mean anything. You will have that it will crash. And when it crashes, you will have an error message underneath say, what is that quiz? What does it mean? So what you have to do in this exercise is to change the word quiz with what you actually want to do there. For instance, in this case, you will need to change this one with the span cube. So the name of the cube for the span and so on for entropy and alpha. So you will see this word appearing a lot in the script, and this is an exercise for you to fill in. This is quite important because it makes this training active for you, not just passively listening to me, but you actively try to do the exercise. But now we can close this one. Just for you to show, if I try to close this one, it will not like, you will say, are you sure? So what you have to do is to shut it down, wait a few seconds, and then close it. So let's go now to the second part of the training where we apply, so we use the actual machine learning methodology. And again, we will be using the same data that I was introducing before, the Sentinel-1, which we pre-processed with the first part of the script, which is also the training that I described in my last tutorial. The level of complexity of the script. So this one is a bit higher and more complex than the first script. So you start doing things that are a little bit more complicated. And my suggestion is that you approach this step by step, line by line. You try to understand what it is, and also try to do the first training before you do the second, you attempt the second one. If you have questions about the code, please ask during the Q&A. I'm very happy to try to help with that. Now again, the same test site, same area. And here, the libraries. We have all the libraries that we used before. Again, if you can install Spectral, although we don't use here, but if you can install it, it will be good. Otherwise, you still can run this code. The difference with before is this bit here, where we are using the Skylearn library. In particular, we are importing these functions here. I use this way of importing functions because then the call to the function gets smaller. So you have less things to write. By any means, you can just import Skylearn, and then all the time you do skylearn.ensemble.random forest classifier. You can do in this way if you prefer, but I prefer to have it a little bit shorter. So you see there are libraries for random forest and for validation and for the k-means. Skylearn should come with an Anaconda installer. If for some reason it doesn't come, then you will need to install it using either pip or conda. If you have a look at the file that I shared in the folder, the Word document, you will find information about how to use Conda to install any libraries you want. Again, define functions. We will need still to use this one to get the dates from the stack, from the folder where our images are. And we can now start loading the NumPy arrays that we saved in the previous step. So the images are located in path save, which is the place where you have saved the images in the previous step, if you remember. Also have a link here to the folder where the original images are. This is to get the dates, the list of the dates. This is the list of all the file names that you use to call our tubes. You remember you have the C11, so the VV, C22, VH, the C12, cross correlation, VV-VH, the span, the entropy, the alpha, and also the dominant alpha. We will not be using here, but still I put it there in case you want to explore adding some dimension to your feature vector. You have these extra tubes you can use for training. So these are the line of code that we actually use for loading the images. You see, it's just a single function load, and you get the tube quite quickly. So we run, oh, we have to run this one first. So I'm running all these cells before, and we are now to this cell here. With this cell, as we did before, we get the list of dates that we will be using in the following. In case that it gets stuck, then you will need to fix it. But in order for you to run this today, I hard coded all the name of all the list of the dates here. So you will just uncomment this and it should work. The first part of applying a machine learning algorithm, a supervised one, is about training. So this is all explaining why the learning part of the word machine learning is because the machine learn how to see the data, how to segment the data, and to do regression using the data. So the first part is about training. This first cell here, I want to set some of the values that we will be using after. Index image is the index of the image inside the stack that we want to use when we are using just a single image, like for visualization purposes. And I set this to the first image inside the stack. Remember, Python starts from 0, not from 1. So 0 is the first element. Seed state is a value that will be used in our machine learning methodologies. You will see later what it is, but I set it on top here so that it's always the same and we don't mess up with that. And here is the number of classes that we want to use. I set it to 4. But of course, you can choose more classes. We can now run this cell, move to the next bit, selecting the region of interest inside for our classes. But since we need to tell the machine how the data look for that class, we need to select our class inside the dataset. And we do that by selecting region of interests inside the data. So what I did here, we just select regions inside the images and small squares inside the image. That you can do straight away. Now, a little note on how Python deal with images. The images are two-dimensional entities, range and azimuth, or dimension 1 and dimension 2. In Python, the first dimension is the vertical one. So if you look at an image, the image visualized in Python, the first dimension, the first coordinate will be the vertical one. The second coordinate will be the horizontal one. If you think about it, this is a little bit not what we normally do, right? If we have a 2D image, X and Y, we'll say the X is the horizontal, the Y is the vertical. So we'll have the horizontal and vertical flipped compared to Python. This creates some confusion in people that are not used to Python. Be careful, first coordinate is vertical, second coordinate is horizontal. Keep this in mind. It's opposite to what you may think it is. So we want to select these images, this portion of the image inside the larger image. What we do, we need to visualize the image as a first thing, otherwise we won't be able to work with it. So this cell visualizes a single image. You see, it creates an RGB, RGB container, three-dimensional, where the first two dimension is the image, the third dimension is the color, RGB, red, green, blue. So you fill this container with the content of your image, and for the different color. Here we are putting the red color is the magnitude value of the cross correlation between co and cross polarizations. The green color is the cross polarization. The blue color is the BV polarization, is the copolarization. Then you need to normalize all to 1, because Python represents images between 0 and 1 when you use this function imshow. So we create this image here. And again, if you want to know more details about that, the first tutorial will explain why we need to do these normalizations. But then we visualize using the imshow function. So once we run this, what you get is this image. You'll see the north-south direction is now horizontal. East-west is now vertical. This is because the Python flipped the two. So we need to flip it again when we want to visualize. But don't be afraid about that. So keep this in mind. Python always flip the coordinates. So now we have these things. We need to select places where we want to call as a class. My suggestion is that we choose something in the sea, something in this marsh area, something in the town, and something in the fields here. How do we do that? We create a row train array composed by 4 classes. These are 4 rows and 4 elements and 4 classes here. Remember, number of classes is 4. They are both 4 actually. The 4 rows here, they contain the start and end of the pixel of interest. In this format here, we start with the first point in range, then the last point in range, the first point in azimuth, last point in azimuth. Okay, so this here represent the coordinates for the first point. So from 100 to 430, and then 119 to 220. This is the second, third, and fourth. You will see these points later when after I run this cell here. One thing that is important is to keep in mind the number of pixels in each row, because this is the size of our training data set, and this is quite important to make sure that we don't make mistakes later on. So by saying last to first in each dimension, then multiply the 2, we know how many pixels we have there. So let's run this one. Then we want to visualize it so that we can see the area that we selected. Remember, when we create this container I RGB, we are actually selecting the 3 colors, red, green, and blue in order. So what we could do here is to take the RGB as we did before. So this is the same code we used before. So it's the same image. And then we overlap a different color in the area related to our class. So the first class, so the one with zeros here, see? The one that ends with 0, the first class, will have a 1 for the red, and we'll have a 0 for the green, 0 for the blue. So it will appear red. The second class will have a 1 for the green. So will appear as green. The third class, so you see the third class, you can see from here, these two here, you'll only have a blue. The fourth class will have all the colors, which make white. So if we run this one, then we see that we are coloring the area of interests here. And now, taking this to the next level, if you want to add more classes, or if you don't like to use these three colors, you can try to use different combination of weight for each color to obtain other colors. Like you can get purple, you can get yellow, whatever you want to obtain. So try that if you want. You can try that. Another thing that you can try after you run this code first is to find different for classes, or selecting a different area of interest, or adding a new class, and see how your classification proceeds. The next bit of the script deals with the random forest, and you will see we approached it in three different ways. In one, the first approach, the first way we applied is by selecting one single image inside the full stack of images. So we have 19 images. We just select one of those, and we run with that. So we run the random forest with that. You can say this is not really making use of the time series. You just select one. You may argue I selected the best one of them, but still you're not really using the machine learning methodology this way. I put it, so sorry, not usually using the time series information in this way. I put it here because it's the saying the first approach, and this also because it's a benchmark for us to see what extra gains you have by adding the time as a dimension, instead of just picking one image and using that. The second approach, we go the opposite way. We go brute force. We take all the 19 images and the 19 acquisitions, and we use them, all of them, inside to train our random forest. This again is the opposite approach. We are using everything. And this may have some disadvantage, as I will tell you later. And then we see another way for doing this, where we synthesize the temporal information inside our time series, and then we use that to train our random forest. So we don't just go brute force, chucking all in and letting the machine decide what is important and what not. We try to understand what could be important and offer this to the machine. So it's, I'd say, an intermediate approach. First bit, as I said, when you want to use machine learning, is creating this training, is creating these feature vectors. So a machine learning approach, what it does is to try to connect some data to, say, a target vector, the class of interest, using a function or a model, call it F here. So try to connect these two. Let's start with X first. X is actually the data to fit, and we normally call it feature vector, although it's not really a vector, it's a matrix in most of the cases. So X contain the samples that were actually measured in the data, so the pixels containing the observables coming from the satellite. Each pixel is generally considered a sample here. In this practical here, we use 5 polarimetric observables, which are the C11, C22, C12, entropy alpha, 5 images if you want. So it means that for each location or for each pixels, you actually have 5 data points or samples that you need to store. We store them as columns, so along a row. So if you have, so say the first row here, for instance, we represent pixel number 1, and you will have the 5 feature feeding to this row here. If our ROI, our region of interest, is a 30 by 30 pixels area, then it will contain 900 pixels, so 30 times 30. So that ROI will have a feature vector, which is 5 columns and 300 rows, because we stick all the pixels in the vertical dimension as rows. Together with the data, the feature vector with the data to fit, we also need to have what is called a target variable. So we have something that we want to link to this function, to this model. This is generally referred as a y, small y, because it's a vector, while the x is big because it's a matrix normally. So if we have 900 samples inside our ROI, if you have 900 samples inside our ROI, then y will be 1 column and 900 rows. And this column will contain the information about the class of interest. Now let's see in our case where we end up when we have 4 ROIs, 4 classes. So the simplest feature vector you can have, say it considers only 1 channel, so only 1 feature, it will be a single column and 900 samples. If you have 4 classes, so 4 ROIs of interest, then you will have that the total number of rows inside X will be 900 by 4. 3,600 rows. As I said before, there is also a function that is linking the data to the class, to what is called the target vector y. And so this is this fx here. We often refer to that as a model. So when you hear people talking about data models, they often refer this one, the link that the machine created between the data and the class that we are giving. Now let's put this into context with what we want to do inside this practical. The most important thing, and this is what is really the bottom line, the most important part of this, is that the number of rows for the feature vector and for the target vector are the same. They both has to be 3,600 in our case. If you have more rows in one case so in say in X than in Y, then you end up with some points that miss a class because there are too many data and not enough class to them. Or if it's the opposite, there will be class for no points, for pixels that don't exist. So there will be a mismatch between the two. The machine learning will crash. It will not be able to run. So very importantly, make sure the two things are the same. Otherwise, it will crash, it will not run. Okay, let's start with the first example using a single image from the stack. And the first bit here, in this cell here, we want to initialize the different parts that we'll be using later. We want to say the number of polarization features is 5, and we want to initialize these vectors here, one-dimensional vectors. I will come back on this later. And also we initialize our target vector. Here we do the assignment. We create these feature vectors. You see, I'm using a for loop where we go class to class for doing that. This is by far the easiest way to get your head around it. There may be more efficient way of doing it, but then things start getting quite confusing. I think at least my head works that by using a for loop, it is easier to don't make mistakes. Also, we are only for classes, so it's not a big deal. It's not a big number of iterations. So what do? We go in the C11 cube or any of the cubes. Then we select the pixels representing the area of interest, the little ROI. This is the ROI represented by the E class. So I, no E, sorry. The I class. I start from 0. So these are the first iteration is the ROI representing the first class, the class called 0, because we start things from 0. This part here represents the image in the stack that we are using. Remember, I set this to 0, the first image. You can change it. But basically, we are going in the cube, going to the first image, and taking the portion of the image inside the first ROI. What do we do then? We use this function ravel to make this 2D little image into a 1D array. Ravel, this is what it does, takes the multidimensional array and it makes it 1D, just stack one after the other, all the pixels. We call these things a C11 1D. Then in this line here, we append these values, this 1D array, to a previous one, which contains our full column of the of the feature vector. In this case, is the column representing C11. So this X train C11 1D is the column of the feature vector, which we call C train, containing C11. So again, what it does, the append, it takes these values that we got from here, this 1D array, and it pushes it at the back, it appends them at the back of this other array, whatever this is. At the start, this is 0. See? X train is 0, doesn't contain anything. So what it does in the first iteration, it put the elements of the first ROI in this array, which was empty before. Now it will contain the first ROI. And append them in the dimension 0, which is the first dimension. Remember, Python starts from 0, not from 1. So it's creating this 1D array. The second iteration, it goes to the second ROI, because I became 1, so it goes to the second ROI. It makes again a 1D array, and this time append this 1D array to what we had before. Before we had the elements of the first ROI. So he appends the second ROI, the values for the second ROI, at the back of the values of the first ROI. Third iteration, go to the third region of interest and append the third elements to what we have here, which is second and first. Fourth iteration, fourth elements, go there, append to 3, 2, 1 elements that we are already here. End of the story, we have all the elements there, stacked one after the other along the first dimension, the only dimension that this vector actually have. Then we do the same for the 2, 2, the cube 2, 2, so which will be the cross polarization. We do for the cross correlation, we do for the entropy, we do it for the alpha. We just repeat things. You see, this is a bit redundant, this code. You can make it more efficient by creating, say, hypercubes, and then styling things them and reading it here. You have less line of codes, but you have also less easiness of reading it. It gets more strange, the code. So I prefer to just repeat these lines and make it easy for you to understand. But you can optimize it in terms of line of code. Then for regarding the white train, what we do, we again start from a white train, which is, there's nothing inside, it's at 0 here. And we append the samples, so the right amount of samples, which is equal to the size of your ROI element. So you go number of pixels of the ROI for the first case, create all ones, and then you multiply by the iteration value here, I. In the first case is 0. So the first 900 samples will be 0. Then we'll append this, the second 900 samples with ones. So we'll have 0, then ones, then this will become 2, and you will append 2, and then we'll append a 3, all the 3s. So we'll have 0, 1, 2, 3, one after the other, again on the first dimension. Here what we do, we get the number of samples contained inside this training. We could get this from this as well. We do from here because it doesn't, you can get it from this information too, by the sum of all the samples here as well if you want. And it creates the full feature vector and then loads the different columns with this 1D array, one after the other. So this now is 5-dimensional and has 3,600 samples inside. Once we have created the feature vectors, we can actually run the model. First things is to create an instance. I think I didn't run this one. No, I didn't run the one before too. I'm missing some cells, so creating errors. Yeah, it's okay. So first things is to create an object called random forest. This is the random forest, basically classified. The model is an object representing the model with an empty model, say, but ready for hosting the model. And the way it does it, but simply running this code and selecting an initial seed for this random state. Now, I have no time to talk about the random forest. I will need one extra section for doing that. We are using a pragmatic way, but please read about random forest before using this so you know what is going on. Bottom line, random forest is called random because there is some randomization there happening. That is the why it's so powerful, because of this thing. And being randomization in with computers means that you have some pseudo-random variables that you generate there. Pseudo-random means that you can set a seed and get always the same results. So the array you get out is random, but if you set the same seed, it's always the same. So each time you run, you get the same. So it makes it repeatable. If you don't do that, every time you run this code, you will have a different classification, different accuracies, different numbers, which are will be a bit weird, right, to look. But if you set a seed, and so you make your generator of pseudo-random variables always the same, then you will get always the same number, always the same classification and accuracies, which is easier if you want to report, also because you will need to report this if somebody wants to repeat your algorithm. So this create the object, and this line here fit the model that connect our target variable y to our feature vector x. So this is creating the model, this simple line of code. A single line of code. You have seen how many line of code we need for this one? Quite a lot. How many line of code for running the model? One. So as I was saying, the difficult bit is to get this thing. Now let's have a look at these feature vectors that we created. If we go on this line here and we run it, it will give us the shapes, so the dimensions for the feature vector, which is 3,600 by 5. Remember, the first is the vertical dimension, so is the rows. The second is the horizontal, so is the column. So we have 3,600 sample for 5 classes, for 5 features for 5 polarimetric observables, while y is 3600. The numbers of rows of these two match, and so we have no issue here. We didn't have any problems. We didn't crash. Now, once we have these things built up, this model built up, we can try to do prediction. So we can try to do classification on areas which are not covered by our training. The trick here is that we need to create, we need to reshape our data set in a way that fits the feature vector that we created. Remember, for creating the X-train feature vector, we had to shape all the files as rows. So the 2 dimension has to become a 1 dimension, and it needs to have 5 columns. So we need to create a container C for our data, which mimic this type of dimension, this type of shape, that is equal to the feature vector. So we start creating the container. So in the most natural way that we'll do, we will contain the first 2 dimensions will be the image dimensions, and then we have the 5 features for our polarimetric information. And then we stack the different polarimetric cubes inside this container here by selecting one index of interest when we want to apply the classifier. Remember, this is only using a single image. So we are only doing this classification using a single image at the moment. So this creates this container, and then we have to reshape it in a way that mimic the feature vector. So we do that by using the function reshape and by saying that the first dimension is equal to the multiplication to the size of dimension 1 times dimension 2, which will contain all the pixels and the number of features of interest. So once we do these things, let's get our head around before we proceed with this. If dimension 1 is 500 pixel, dimension 2 is also 500 pixel, this new x underscore variable will be 250,000 rows in size and 5 columns. So it will be 250,000 by 5. This will be the dimension of C underscore, because you have stuck all the elements of our image in a single dimension. Once we have that in the proper format, we can feed directly to the random forest and ask for prediction of which class this pixel should be. To do that, we use the function predict. So the argument of the function is this new shaped data, our data shaped in this format, and the output will be the class they belong to. So this y hat underscore will be 250,000 in size. So it will be 1 column, 250,000 row. That is not what we want to see. So that's not what we want to visualize. To visualize it, we need to reshape back to what it was at the start. So again, we use the function reshape for this y hat underscore, but now the dimension will be dim1, dim2. So we go back to what we did before. Before we reshaped in dim1 times dim2, now we reshape in dim1 and dim2, 2 dimensions. As long as this is correct, so as long as the number of pixels at the end is the same, the reshape will be happy. It will give you the new array. If that is not correct, so if like here you say a +1, then it will crash because the 2 dimensions don't fit. Okay, so the 2 has to fit. As long as they fit, it will be okay. And so we get a classification map using one date. and we can visualize it using this code here. And this is how it looks like. Quick look at these results. We see the sea is quite well classified. The marsh area is also quite well. The city is a little bit of misclassification, and also the sea is a little bit where it shouldn't be. So it is okay, but maybe it's not the best. If you use different area for training, a different image in the stack, you may get a better results. But yeah, there will still be some issue there. There will be some ambiguity because sometimes the sea look like the land inside the SAR image at a single date. Here is where we want to check this dimension. This is more for you to get your head around what is going on. You see the sea, the full container is an image of five elements. And then it became this 250,000 long feature vector. Then I had the two match in terms of length. And after we do the classification and we ship back, we have our 500 by 500 back. Always make sure these things coincide, they are correct. Or otherwise it will crash most likely. Next things I would like to tell you and would like to show you inside this script is where we try to assess the accuracy of our classification. So we try to do what is called a validation. This is an essential step. When you run some machine learning algorithm, you should always check your accuracy. You should check that it's doing things well. And there are several ways of doing it. If you do the wrong way, you will end up having extremely high accuracies and not really inside the data. So you change data set and the classification map will be horrible. So you really need to be careful how you assess your accuracy. Here I show you a simple way because I'm only using the ROI that we considered before. But if you want to make this more powerful, you may want to consider ROI also in other data sets, in other places, keeping, of course, constant the timings and the, say, incidence angle and these things, but you want to make this a little bit more general. Here is very specific to the small area. We are doomed to have very high levels of accuracy. But it shows you the way you do it. So it gives you the tools to be able to do this and take it to another level. So the first things is to split. The simplest way you could do it is to split your training data, so your area where you know what is going on, inside a test and a training area respectively. So normally you use 33% for test and the rest for the training, so 67 in this case. So more training than test. A way that is better is possibly to do cross-validation. So to split again in this 33-67, but doing it many times. And in here I will show you a threefold. So you find three ways, or the machine actually finds three ways to split this data, three completely independent ways, and then assess the accuracies for each one of them. And if you have not enough data, you can also say leave one out. So you always take one sample, train with the rest, and test with this. Then again, take another sample, train with the rest, and test with that sample. That is leave one out. So it's the extreme of this cross-validation. When you apply this type of validation methodologies, you generally find out that your accuracy go down. Because this one, generally you find out that it's more complicated when you do these things. So what we represent here is the accuracy, which we define as the correct classification divided by all classifications. So it tells us how many right calls the algorithm has over all the calls. So how many pixels are good, are well classified, basically. It is the, say, possibly the simplest way to do this, and there are other ways more powerful, but this is the most clear and possibly the most straightforward, and most people use it. So that's why I include it here. But I also use a confusion matrix, as you will see later. Now, how you do the split? Likely, Python, the sklearn library of Python has some functions for doing that. So we use the function train test split. Here, what you do, you write your feature vector, your target vector, and how much you want to have the split. You will say 33%, and then again a random state, so that every time you run it is the same. If you want to share the code, also the person that will run will get the same result. And what you get out is a split between a train, this one, and a test area for both feature vector and target vector. Then what you do, you create a new model, object random forest, you train with the train part of your split, and you produce the results of the test area by predicting using the test. See? So we trained using the train, and we tested using the test part that we obtained here. And then we use this function, so this one, sorry, accuracy score, to tell us about the accuracy. And we need to give the results of the prediction and the actual value that we have there to get an accuracy. Also, we can get a confusion matrix that tells us where the error comes. And here we do the cross-validation part, where we say that we want this to be threefold, so repeated 3 times. And if we run this, these are the results. The accuracy in the first case is very, very high. The confusion matrix is this one. And to read a confusion matrix, when you look at the confusion matrix, you see where we make mistakes. Like there are mistakes in class between class 1 and 2. There is some mistakes. The 6 here are misclassified. So it tells us where you make the mistakes actually. And the threefold give us this result here. You look at these 3 accuracies, you see they are lower than this one. It is what you expect. Normally, what people do is average these 3 to give a final accuracy. In this case, will be around 0.96. What I would like you to see is that your results, the accuracy that you get, is really sensitive to the way you select your ROI. You move your ROI a little bit, and your results is very different. So this is because we are using very small ROIs, and so that is not ideal. You want to have a better way of selecting the targets. But in general, the results you get from machine learning is really strongly dependent on the area that you select for training and test. Then the second part of the script consider multiple dates. The easiest, the first case is when we use what is called brute force. So we just give everything, all the pixels as they come to the machine, and we let the machine figure out if there is patterns there, how to find out the patterns. And this is the, say, possibly not the approach that I like the most, because there are ways you could format the data so that it's better for the machine to then extract this pattern, find out the patterns. If you give everything, sometimes there will be mistakes coming out. So that is my approach. You can have a different approach. You may prefer brute force. It is up to you. But here I show you how to do it. So we have 19 dates here and 5 polarimetric features. The easiest way to do this is to use to add new columns every time we add features. So the first 5 columns will be the features, will be the polarimetric feature observable for date 1. Then from 6 to 10 will be date 2. From 11 to 15 will be date 3, and so on. So you stack them horizontally as columns, all the dates. If you do that with 19 dates and 5 polarimetric features, you end up with 95 columns or 95 features for your vector. Here is where we do it. First of all, we want to understand how many features we will have at the end. With this time series approach, we have number of acquisition multiplied number of features. And then we create again this container. At the start, it doesn't have any samples here. It's still empty because we want to fill it in. And then the easiest way to do this filling in of the feature vector, I find is by using two for loops. Two nested for loops, one in the other. The first one is for the number of acquisition. The second one is for the number of classes. You remember this part here is basically the same that we did before. But now, because we have more acquisition, we have to nest this inside another loop, which works for the number of acquisitions. Again, you may find different ways of putting these things together. We relies less on for loops, but I guess for loops are the ones that are more intuitive, and that's why I'm using them here. So the first for loop is about the time we are selecting. So we start with the first acquisition, so j equal to 0. And then what we do, we create these one-dimensional features as we were doing before, just the same thing. Then we start the second loop, which is on the number of classes. Remember, is what we were doing before. So we go on the initial cube, the first cube, C11. We select the index for the first acquisition. Remember, before here we have the index of the image. Now we substitute with J, which is the index running over all the images. And we select the part of the image inside the row number 1, because I is equal to 0 in this case. We ravel, so we make it 1D, we store inside the C11 1D, and we append to these vectors, which we have been initialized here as 0 vectors. So as before, we go first come class 1, then class 2, the pixels for class 2 get appended at the back of class 1, then class 3 at back of class 2 and class 1, then class 4 at back of class 3, class 2, and class 1. Lead your attention on the fact that we are piling them up in the first dimension, which is the vertical dimension. Remember, samples are in the vertical dimension. We do the same for the element, for the image C22, for the cross correlation C12, for the entropy, and for alpha, just as we were doing before. We create again our target vector here, same way we were doing it before. And at this point here, we load all these one-dimensional vectors inside this X-train temporary vector. This X-train temporary will have a number of rows equal to the number of samples we are considering, and 5 columns for the 5 feature vectors that we are adding here, these one-dimensional features. So it is not the full temporal feature vector, is a temporary one considering one single date. The full feature vector comes here. So what we do, we take this temporary feature vector, which is only 5 columns, and we append at the back of the final feature vector in the second dimension. See, axis equal here is equal to 1. So we are doing the append in the horizontal dimension, so along the columns we are appending it. Not anymore as samples vertically, but as features horizontally. So be very careful on these values here because it really change a lot what you're doing. And also this is the bit where one has to get the head around how to pile up these feature vectors. End of the story. We have piled the first image, the feature vector, the first image inside this vector which was empty at start. Then we go second acquisition. Again, we initialize these 1D vectors. We do all the for loop for the 4 classes, and we obtain again another X-train temp feature vector temporary for 1 acquisition. We pile it with an append on what we had before. So now we will have that the first 5 column will be time 1, first acquisition. The second 5 columns will be for the second acquisition, because we are piling up along the horizontal axis. Axis equal to 1, which means horizontal, is what you will call 2, because Python starts from 0. Next acquisition, you will pile up the third acquisition to the columns of the second and the first. Fourth acquisition, you pile up at the bottom of what you have for 4, third, second, and 1, and so on until the 9th acquisition. So all of them, one after the other, you pile them up. And at the end, you get a vector which is with 95 columns. So we run this one, and then we want to check that we are right when we're talking about these dimensions. So we see that the single 1D feature vector is just 3600, just one single column. That this one contains C11. The target vector is just a single column, as before. The temporary one is considering 1 acquisition with all the features. So it will be 3600 times 5 columns. The final one, which is this one for the time series, TS, it will include 95 columns. So 3600 by 95, which is what we want at the end. So once we have our feature vector sorted, we can again run the classifier here. And you see the same way. You just change the feature vector you put inside, and you just get the same. To do the classification, so the predictions, we need to rearrange our data in this very big cube with the 95 features. So what we do, we create again a simple one for 1 acquisition, a C for 1 single acquisition, and then we reshape this into what has in the bigger one, in the one that is like we did before, you remember? So we make the 2D image in the say 1D image for 5 columns again. And then we append this to what we had before. So we do the same processing we were doing for the feature vector, but this time with data. Again, pay attention to append it on dimension number 2, so axis equal to 1, which is the horizontal one. Otherwise, you will append the other dimension, it will not work, it will crash. So it has to be columns. But once you have done all this bit appending and creating this huge data, huge say data frame, what we can do is to run the code. But before we do that, let's have a look. This one. Let's have a look at the dimension of these things. So we will have that the new reshaped data set will be 250,000 rows and 95 columns. This includes absolutely all the data that we have, all the dates, all the polarimetric features. The CV which is the one for one date, is 250,000 by 5, because it's only a single date before we append to the big one. And C, the start one, is again 500, 500, 5. So before we do this reshaping to make the image into a line. Once we have this, we can do the predictions and we look at the results. Look at the results, they are better than before, although the city still has some misclassification, but yeah, they are improved a tiny bit from what you had before. But it is hard to say this thing by just looking at the images. We can do the validation. You will see here, it is exactly the same that we were doing before. It's the same line of code, I only changed the names of this variable that we put inside. So we split our areas of interest, our ROIs, into 33 for test and 67 for train. And then we train over the train part of it, and we test, we predict over the test part of it, of these samples. And then we can calculate accuracy and confusion matrix. And we do also a cross validation to have a bit more robust way to see this thing. You see the accuracy has improved here, and the results you see are, again, for the cross validation is lower than when you do you just select one, but they have improved. So you have a better classification. Now this one may look quite ridiculous to some, and indeed it is. If you use a bigger data set, if you try on more images, you will not have one there. Is this because you are using small ROIs and a single image? It is very easy for the machine to do it. But you have to be careful when you get these accuracies to make sure that your ROI are constructed properly. Otherwise, you get ridiculously high accuracies. But anyway, it's higher than before, so there is something we are adding there. The next step of the script is by using the synthesized multitemporal information. And the idea here is that you don't stack the 19 images as brute force inside there, but you try to synthesize it in a limited amount of features. So not 19, which show the full trend, but in this case it's 2, but you can have 4 or 5, which are some characteristics that represent this type of trend for that observable, but without using the actual values for it. Why you may want to do that? There are some cases, like in agricultural, for instance, where you may have the same target, the same type of crop, say barley, is actually seeded at different times. So the sowing happens at different times, quite different. If this happens, the time series for field A may look delayed compared to the time series for field 2. If you try to do classification, the machine will see field 1 and field 2 as different. This may be fine because you may want to separate the type of agricultural practices, or may not be fine because you just want to know where barley is. So once you use the full time series in a brute force, you may risk to have this issue when there are delays between the trends of different targets. But if you consider a synthesized information, for instance, you consider the mean, the standard deviation, minimum and maximum, and there are other things like the temporal entropy, other things that you can consider. If you do that, then doesn't matter when the process starts, these values will be the same, say, or very similar. So depending on your problem, brute force may not be the cleverest way to do it. Maybe you still have to help the machine a little bit to see this pattern by adding, by using a different way of formatting your data. What we do here, just as an example of what you can do, is by using the mean and the standard deviation. So very simple, is the simplest you can get, but it tries to, to step in that direction where you synthesize the temporal information before giving to the machine. And it's a step forward to using just one image, because it's using mean and standard deviation. But also you could add more features, for instance. 2 maybe is not enough to get the best accuracies out. But it's a start. So again, we consider the mean of an observable, say C11, by calculating the mean over the cube. And it's important to tell Python on which axis we are doing the mean. Axis 2 means that we are doing the mean over the third axis of the cube. Remember, the cube had first 2 axes were the dimensions. The third axis was time. So we are averaging over time. This is the time mean, time average of the C11 images inside the stack. We do the same with the standard deviation. Standard deviation over the time. Then we repeat it for C22, for C12, entropy, alpha. So all our observable, all our polarimetric features. Again, we need to initialize our target vector and initialize these 1D vectors. There are several ways you can do it. You can pile this thing together into cubes and then feed the cubes after. I do the simplest you could think about, which is considering different 1D features for each of these, say, temporal features that you are considering. So there will be a 1D training feature for the mean of C11, one for standard deviation, and so on. What we do here, as we did before, we have a for loop over the classes we are considering. And this, if you look at this, is identical to the one with a single image, with only difference here is that we don't have an index for the image, remember, and we have this double of the features we were having before. We have mean and standard deviation for each one of the polarimetric observable, but for the rest, it's identical, you will find. So we pile up all these 1D features. Here we create again our target vector. Here, as we were doing before, be careful to append on the axis equal to 1. Sorry, the first axis, or axis equal to 0 for Python, which is the vertical one, where our samples go, the vertical axis. And here we build all this inside this feature vector, which has now 10 dimensions. It was 5 before, but before we extracting 2 time features for each polarimetric features, we have at the end 10 features in total. We can run this, and then we run this one to look at the size of these things. If we consider the 1-dimension temporal and polarimetric feature, we have 300, is a vector, vertical, so a column vector of 3,600 samples. Our target vector is also 3,600, just one vector, a column, while our synthetic one is 3,600 times 10 columns, because we are considering 10 features combining polarimetry and temporal information. What we do here, we fit again the model, same than before, we just change the name you put inside here, and we test it in this line here. And what we do here, we select all our, so we create again this big container with all our features there, and we reshape it so that we can feed to the machine. Then we do our predictions, and we the results of these things we reshape so that is equal to an image again. And this is our result. And if you look at this, you may argue it's a bit better than the other one. And the from just a visual look, where the CTC is a little bit reduced. But yeah, it is at this point it can be a little bit subjective because we don't really have a fantastic training data. So we just select this on the image by eye. And again, my suggestion is that you look at the 3 results and you try to compare. But what we do here is to run the accuracies, same thing than before. We just change the names of these things, and you have that the accuracies now are very similar to the temporal one, higher than a single image, which is what we are happy about. So it's better to use the stack and not single image. But at this stage, they are similar to what we have with the 19 features, 95 feature in saying the brute force approach. And you will need better training data to be able to see differences between these two. Okay, so that is the random forest finished. And here there is a bit of suggestion of things you could try to do, like make this into functions, make this code a bit more modular. And my suggestion is that you do this using Spider instead of this one. So you create these libraries, and then you call the libraries by importing them. But it is up to you. It's something to make it a little bit more automatic and more, say, operational. What I would like to do now, if you have the opportunity, is also to think a little bit about that. So how do you assess this random forest performance, the performance of the random forest algorithm? How do you think it was? Of the 3 approaches, which one do you think is more appropriate for your specific application? And why these things is happening? How you could improve results in your case by producing a better feature vector that will suit better your specific scenario, and things like that. If you have the opportunity to discuss this with somebody else, that will be great, so that you can also share your ideas. Otherwise, just reflect on how you can take this and make it useful for you with your data set. The last part of the script will be quite quick, and just want to show another type of algorithms that we could use, which is unsupervised. So it does not require us to select this row inside the images. We just give the data to the machine, and the machine will tell us the classes. We just tell how many classes we want to have, and the machine will care for all the rest. Possibly the most popular of these unsupervised classifiers is the k-means. And this is the bit that you will need to create to initiate this object k-means. So you need to tell how many classes you want to have. In our case, it's 4. You want to tell how you want to do the initialization, which is random, how many times you want to repeat it with different seeds, so to get your results, the maximum number of iterations for each one of these iterations, the tolerance level, and the initial random state that you want to have. So to make it, say, repeatable. So every time you run, you get the same result. So here we see a little difference from what we were doing before. Many machine learning algorithms will need our feature vector to be normalized or standardized. This because they're based on distances between these points, these vectors in their feature space, and standardization generally help weighting the features in a better way. Otherwise, one feature may be having more weight than another when the distances are calculated. Random forest doesn't need that. The way it's built, because it creates these trees, it doesn't really need this standardization, this normalization. But many of the other machine learning algorithms do need it. So I also want you to show you an example here with a k-means that does need this kind of, can be improved by doing this standardization. So what we do here is to take each of the features for instance, the C11, then we subtract the mean and we divide by the standard deviation. And we do this for all the features of our feature vector, and then we run the k-mean with this function fit predict. See, we don't need to train because it's unsupervised, so we just need a single function call to do the classification. What comes is one-dimensional, then we need to reshape in order to make it similar to an image that we can visualize. And the results is what you can see here. You see, it's not better than what we were doing with supervised classification, like the yellow is supposed to be the C, is a lot here, but it's in unsupervised. Really, the machine is trying to find a pattern inside the data on its own. It can be quite useful as a step before you really start your supervised classification later, so it can be quite useful. And in some cases, we want to do the same for the case of time series. So again, we normalize the features and we produce our big data frame or big feature vector like we were doing before, and then we can run the fit predict and obtain an image, obtain a classification map. This one will take a bit more time because the data is big, so it's really calculating a lot of distances in order to perform the classification. So it may take a little bit of time, but in the meanwhile, while this process, I can show you the last bit where we again use the data with the synthetic temporal information, and as before, we normalize, and then we can feed to the k-means algorithm here, which I will run here. If we have a look now at what we obtained using the time series, you see the result is a bit cleaner than before, less noise in that when we were getting here, but still there is a little bit of confusion because the machine doesn't really know what is what. It doesn't have, so it may confuse the water with inland areas. And this is the results where we acquire with the synthetic information, which again is a bit better, but there is a bit of confusion there. Nevertheless, this type of unsupervised algorithms are useful sometimes, and you may want to exploit them in some situations. That is really all the code is finished now, and I would like to finish this with this bit here. So I would like you to think a little bit about this k-means classifier and how it compares to the random forest one, and try to get your head around when you could use a k-means, when it could be useful for you maybe as an initial step to then go to a supervised classifier, or if it's completely useless for you. Just think a little bit about it, the potentiality of this type of algorithm, and when you may want to use it. Take this to the next level. You have seen here how to use random forest and k-means, but there is so many other machine learning methodologies you could use, even just inside the sklearn library. For instance, you can have support vector machines, neural networks, and many others. You will see that as long as you have a pixel-based classifier, so means one pixel, one sample, then you can really apply all these things by just changing almost a line of code, 2 lines of code, and you apply a new classifier using these libraries. What I suggest you is to try more than them. Random forest is normally considered a good one and often give the best results, but not necessarily. In some situations, it's not the best. So you may want to run other algorithms and see how they compare as well. What we didn't cover today is deep learning. If you want to use deep learning methodologies, then the thing is different because you use imagejet to train. So you don't use a single pixel for training. It's like object-oriented type of thing because it's based on these convolutional neural networks. So this was not covered. Maybe in a future practical, but not here. So this will not allow you to run those algorithms. But once you have learned how to use the pixel-based one, doing a step to this other deep learning, it won't be that complicated. The step is not as big as you can think once you know how to use the pixel-based one. So, and in this, have a look also at other areas inside the data set, and play a bit around with this code. If you have any issue with these things, please ask your question. I will be now answering. After the session, I will be answering the Q&A. I will be answering your questions. And I hope you enjoy using this data, this methodology. So I would like to thank you for your attention, and also I would like to acknowledge the data providers. In this case, is the European Space Agency. Thank you very much.
Armando, thank you for the wonderful presentation and demonstration. We will now transition to the question and answer portion of today's training. Please enter your questions in the question and answer box, and we will get to them in the order they were received. We will post the question and answer document to the training webpage before the start of next week's training. Below is the contact information for Dr. Marino, along with links to the training webpage, website, and social media. If you enjoyed today's webinar, we hope you will sign up for the ARSET listserv to receive notifications of future trainings, and follow us on Twitter for other relevant announcements pertaining to NASA's Earth science.
I want to thank everybody for submitting such wonderful questions. And again, we do encourage, if you have any questions based on what you've heard today from Dr. Marino, please do submit them to us, and we'll try to get to them before, looks like we have about 30 minutes left. So we'll try to get to as many as we can in the next 30 minutes. So Dr. Marino, question number 1, is it possible to follow the PoISAR approach for urban classification, or is it only recommended for different vegetation types areas?
First of all, thanks for this opportunity. So let's go to answer this one. Yes, you can do urban area classification, or generally PoISAR applications. There are quite a lot of them. One thing that is quite curious is that possibly the most famous training data set ever used by the PoISAR community is in San Francisco. It's about the city and also the sea surrounding and the forest. So definitely you can use, and especially gets very powerful when you combine it with interferometry. So you do what is called PoISAR, because you also have some information about the elevation of your target. And mainly application on urban are related to change detection, so the buildings, new construction, say a new land change type of things, but also classification, the type of urban area as well. People can classify the type of settlement as well. So it's a quite a lot of people work on that.
Great. Question number 2. There are some similar pixels in the RGB SAR image in your slide. How do you differentiate agricultural fields with that of marsh or even wetlands?
Yes, this is also a very good question. The first thing that I would like to say here is that what we see in an RGB is just 3 channels, a red, a green, and a blue. But in PoISAR images, you have much more. There is more information there. You have seen in this tutorial today, we extract 5 observables, and here we are only plotting 3 inside RGB. So my, say, a note of caution is that when you look at these RGB, which are beautiful, don't think all is there. It's like a a spectral image, multispectral images. It's not all there. There is something hidden that is not shown in that image. And so explore more than just the RGB. But RGB are very useful to try to get a feel about what you have there. and there is for sure an ambiguity between different targets, especially if you see a different time during their, say, phenological stage. So you say you can have a type of width, that sort of month of the year, which will look exactly the same of, say, grass or something different. So there will be ambiguities, that is for sure. What I wanted to show here is that by using temporal information, so by looking also at how these things evolve in time, you can get extra information and understand better which is the type of target. For instance, maybe the grass will stay more or less stable, the wheat field will change a lot, acidity will be very different as well and very sort of stable, and so on. So temporal information, I think, is the key. Otherwise, you will always have ambiguities, even with quad polarimetric data. There will always be ambiguities between some type of target, which just look the same. But you should not be too surprised. In optical, is the same. You take a Sentinel-1 image, so not very high resolution, and sometimes you cannot really tell what is there. It's very complicated, you know, there as well. So go for temporal data.
Okay, wonderful. Question number 3, can we map crop damage using Sentinel-1?
That's a very good question. And so you can do something similar to that. The people are working on detecting anomalies into the evolution of some crops. So you need to build a model of how that crop is supposed to evolve in time. So the different, if you want, colors that will assume in the RGB, so the different characteristics, polarimetric characteristics, although there is more than the RGB, but to tell you, so the different polarimetric characteristics in time. And then once you have this model, you can look at your data now and see if your crop is following the trend that you suppose it should follow. So you do something called like Gaussian filtering is one way you can do that. And then if there are, or the Kalman filter is the famous one, if there are differences between what you have and what you expect, then you say something is going on inside that field. So indeed, yes, you suggest you to, so it's something you can do. It's not as easy as what we did today, but it's feasible.
Great. Question number 4. Is it the same definition of the dual polarimetry decomposition as coded into SNAP?
Yes, it is the same code, not the same type of decomposition, which is also developed in SNAP by using Java. So we use Python, but that's the same thing, yes.
Great. Question number 5. Can you please explain saving the input image stack as binary NV format? If possible, please briefly show how.
Yeah, this is not too complicated, but it was too much for doing in this training. Also, one issue is that if people could not install the library, they won't be able to do it. So that's why I removed it. But it's very few lines of code. Here I put a link where you can see how to do it, and it's really very few lines of code. The important there, so the things get very simple if you extract, so you read an image, an MV image in Python, and then you obtain some added value product, your map, and then you export this again in MV, the same image with the same number of pixels, and then it's very easy. It's just 2 lines of code. If you start modifying the size of the image and you play with these things, then the image will be distorted. You cannot do it anymore. It's more complicated to do it. But if you really want to do things that are a little bit more complex than just that, so read the image and then get the output with the same format, then my suggestion would be to install GDAL and to do this the hard way, but also the more robust way, that you have more control of things, and you can also, you don't have to export in MV. You can use, I don't know, a GeoTIFF, whatever you want to use. So yeah, easy if you do easy things, get complex, and then suggest GDAL if you want to do more operational things.
And question number 6. Can you explain the data preparation stage, please? Also the format of data.
Yeah. That's a good question. And I can direct you to the previous tutorial that we were doing. So I think 1 year ago, I can remember. We did on this. So if you, so that is basically the tutorial we were suggesting you to see before starting this one. And if you go on YouTube, on YouTube video, you should find it around minute 30. So there is where more or less you find what we do, all these passages. And yeah, it's quite a lot of things and require quite some time. So for the sake of time, I will direct you to that instead and explain it now.
Wonderful. And I'll also add too, in the slides that are on the training webpage, on the prerequisite slide, I forget what slide number that is, we do have links to all of the previous trainings that we strongly encourage all the participants to go to if they want any background information, especially more on the theory of SAR polarimetry. We have all those links for those prerequisites, and we do encourage you to go check them out. So question number 7, which SAR indices will you recommend to map and monitor crops from Sentinel-1 data?
Mm-hmm. This is a very interesting question, very topical. See, there's a lot of research going on this at the moment. So to try to find what are the best vegetation indexes to describe your type of specific type of crop. Again, there is another tutorial on that, so you can redirect you to the previous training. But I can give you my 2-penny contribution here very quickly, but you will learn more from the other tutorial. And it really depends on the type of vegetation you are dealing with. So the type of scattering model, polarimetric scattering model, that best fit that type of vegetation. Some indexes are more sensitive to a certain type of model, some others are sensitive to another type of model. So I think there is not really one that performed best. You will need to to check what you have on your data. So to try several and see the one that gives you the best accuracy.
Great. And as stated in the first line of the answer, we will be covering SAR vegetation-based indices in part 3 of the training. So we do hope all of you will be able to join us for all 3 parts of this webinar series. Question number 8, how to run Snap GPT graph using Python. Can you please provide any small example or used in this for generating inputs for this tutorial?
That is a good thing. So that's a good point. So using the GPT is quite powerful because what it does, it takes you out of the process of being there in Snap and running the things manually. You can do it all automatically. It is really core if you are doing something like inline processing. You get a new image, you want to go, that goes inside your pipeline, you need to get an output in 6 hours. So you cannot be there every time a new image arrives to click on Snap for doing it. If you don't have any requirement in this context, that you can simply run the Snap batch processing. So you go there, you have your graph, you put everything inside, you click run, and then come back on your machine a few hours later. That is, you can do it. It's allowed. It's okay. But if you want to do all inline, so that does automatically, new image come, get out, then this graphical processing tool is really the way to go. It is a little bit fiddly at the start because sometimes, especially when it crashes, it's hard to debug. I would redirect you to this training on YouTube so you can start having a look at what it is. And when you debug your code, make sure that the graph works very well in Snap already. So try it for batch processing CO2 images and see if it works okay. And then you try to approach it in Python. Most of the cases, Python will throw errors if the file names are wrong or the folder is wrong, and it will be very hard to understand that is the error because it's not easy to debug. But when you're sure it runs well in Snap, then it's a good step, and you can try to implement it in Python. And it's really few lines of code. You're talking about, I don't know, 10 lines of code for doing it, but you need to be careful on the way you approach it.
Okay, question number 9. Is it possible to extract these parameters using PoISAR Pro software using a batch processing tool?
Yeah, very good question. Yeah, PoISAR Pro is a very powerful software for polarimetric data developed by Eric Potier in RAIN. So indeed, you can do it. Do batch processing of PoISAR Pro is a little bit more complicated than doing it in Snap, but it's still very feasible. You can definitely approach that. The good things of PoISAR Pro that you find processing that are, say, better for quad-pol because they're not included in Snap yet. So they, you will find the composition that you will not find in Snap. The crop here you also find in Snap, but others you won't find in Snap. But PoISAR Pro has it. So that you can try to see how to implement this routine batch processing. You can try to find the way, but also I want to let you know that at the moment we are converting PoISAR Pro C routines into Python. This will sit in the map platform. It's a collaboration between NASA and ESA, where there will be all these say routines, Python. The data will be there, especially in ISAR and biomass. The data will be there, and so one can really harness the cloud computing and cloud storage, and you don't really need to download stuff, and you can run your Python code there, and the Python code that we will put there. And among other things, there will be the routines for PoISAR Pro. Now, I said still at the start of map, so you will need to wait maybe 1 or 2 years before seeing it happening, but it is getting there. We are working on it, and hopefully you will find it useful in the future.
Terrific. Question number 10. Can we use Earth Engine Python API to execute this exercise? I mean, using the Google Earth Engine Sentinel-1 catalog and not downloading all the images.
Yes. So here the answer is yes and no. So this specific exercise, then the answer is no, because on Google Earth Engine, you only find the GRD, ground detected images. So these are the images, the intensity images without the phase. To do what we are doing today, you need SLC, single look complex, which also has the phase, and so you can do the correlation between the two polarization channels. This won't be possible at the moment in Google Earth Engine. The data are not there, but you can of course upload your data, your SLC, in Google Earth Engine and then run it there. So that is a possibility. You need to see if you want to do it. I think the good thing is that you don't have to download, and also the processing, it helps, but the processing time. But the good thing is you don't download. But if you have to upload your data, you have to download them before. So maybe that is not you don't make great use of Google Earth Engine. But if you have all your, say, processing stack, all your presentation of data, the thing you use for you with your stakeholder is in Google Earth Engine, then there is a possibility to do that. Another thing that is really useful and is coming up, say, more recently is this Google Colab platform, collaboration platform. There you run Python. So in Google Colab, you can run the script that you have now that I made available. You can run it in Google Colab. It's a little bit like a Jupyter notebook, but you can also run the .py, so it's not just the notebook. The thing there is, again, you need to upload this data, so you need to put them on Google server before you run, but then you can use cloud computing. So if you have limitation in terms of computation, then Google Colab may help you. Also, I think you can, if you pay premium, you have faster processing as well. So it is really a cool things, and possibly we will see more about that in the future. So if you are trying to harness cloud computing with Google, then it's Google Colab where I will point you, but you will still need to download the data at some point until Google decide to put SLCs there.
Great. And question 11, I'm just going to talk through myself. It looks like one of the participants got an error message in their code using the NumPy integer function using NumPy version 1.24.1, and this participant was able to troubleshoot and resolve this issue by replacing the numpy.int with numpy.int64. So if anybody else is getting that error message, thank you to that participant who was able to troubleshoot that and share it with everybody. So again, all of these question and answers will be uploaded to the training page by next Tuesday. So everybody will have access to it. So question number 12, is there a way to directly download data from the ESA website using APIs?
The answer is yes. You can use these APIs that are available, and then you can say automate your download. Also, you can do a request. This ask, is there a new image? And when the answer is yes, you download or you don't. These kind of things. You can be very clever in making these things more operational and making this say inline for the inline processing. If it is not inline things that you needed to do, so then if you just need to do batch download, then maybe my suggestion is to use the Alaskan Satellite Facility that very easily allow you to create a Python code. You create this for you, then you just need to run this code on your machine and download start. It's really super easy, and you can see a link there how to do it. Otherwise, batch downloading by clicking on each one of the images is a nightmare. When you have lots of them, it's not something that I don't suggest doing if you can avoid it. But there are ways of doing this batch download, as you will see in the ASF website.
Terrific. Question number 13. Can you please specify which versions of the libraries you are using for sklearn, numpy, scipy, etc.?
Yeah, yes, I was checking as well. I didn't remember the exact version, but the sklearn I'm using is 0.19.1 and the numpy one is 0.14.2. If you download Anaconda more recently, you will have bigger numbers there. But if you did in the past, you may have smaller versions, so smaller numbers, more recent, older versions. I cannot tell about the older version, but the new version had people with more modern version than mine that ran it was okay, so it should work. If you have something before that, it may not, so you may need to get the new versions.
Question 14, how do you clip the exact same subset area? Because I think there is some shift, sometimes up to 1 pixel, between different images.
Yeah. This is a very good point. To create this stack of images, you need to do some co-registration. So if you just geocode the images by using, even if you use the precise orbits of Sentinel-1, you may still have a little bit of a shift. It's not perfect. So say a pixel is something that you can easily have. So the georeference in itself try to do its best, and it's very good most of the time, but sometimes there is a little bit of a shift. You need to correct for that and make sure that all the images overlap very well on top of each other. And this is done by doing some co-registration. You will see a link here where there is some co-registration for Cosmos Skymed, is a different type of satellite, and also is done for interferometry. So the co-registration they do there is the good one, the one that will allow you to do interferometry as well. For doing PoISAR, Polarimetric SAR, we have less strict requirement when it comes to co-registration. For us, a shift of almost a pixel is sometimes acceptable because in PoISAR we do averages and then we consider that we overlap the different images without calculating their correlation. So like what you do in interferometry. So you have a covariance matrix for each image in the stack and you use that. Now, if you shift of almost 1 pixel, your covariance matrix will not change that much because you are doing some average there. So you are considering many pixels inside. Still, you cannot accept a shift of say a couple of pixels, but a very little one you may still be okay if it's PoISAR. If it's interferometry, not at all. you will not be able to do anything. You really need to be super precise. They're much smaller than a pixel. And so try to give a go. So if you want on your data, try to give a go with this co-registration stacking of images. Don't forget about that. Otherwise, the images will not overlap. You will see very weird things in your data. It is an co-registration is an essential step when you want to do multi-temporal analysis.
Terrific. Question 15. I'm not sure about defining the file paths in part 3.1 of the PoISAR time series document. Should I set it up with the cubes or the imagery?
So in the first file, so the time series file, where we create the cubes, then the pointer, so your folder should point to where the images are. In the second file, one that has the ML in the file name, then you can point to where you saved your cubes, so where the cubes are. But in the first one will be the images. And make sure, if you are getting errors there, make sure you put the double slash at the end, make sure you use two double slashes if you are using Windows and all these kind of things. But it should be that one, the folder.
Okay, question 16. Is there a maximum number of vegetation classes?
Mm-hmm. That is a big question. And in theory, yes. So the more classes you add there, then the harder your classification task became. So it gets more complicated to separate the different crops. If you have just one, say, crops, it's easier than if you have 10 type of crops, or 20 or 30 or whatever. But it maybe is too much. But anyway, if you have many of them, then it gets really more complicated. There are also some crops that are pretty similar. They're pretty similar even optically. You look at them, if you're not an expert, you won't be able to discriminate them. Like the cereal, for instance, they're quite similar to each other, and often you have errors inside your classification will have errors there. Then you classify all inside a single class, and it gets all higher accuracy. So it really depends what you're trying to do. My suggestion is that you try to start slow and then try to include more and more if the accuracy are still okay, and then produce some confusion matrices to know where you make mistakes. So then once you go to your user and say, this could be this or that, because these are where we don't really know exactly. So to get some extra information from the confusion matrix, and that as many as you can deal with. Yeah.
Wonderful. And we are reaching the top of or I guess the conclusion of this webinar series. We just have 2 minutes left. Before I wrap up, Armando, Dr. Marino, I was wondering if you had any closing thoughts or anything you wanted to tell the participants that are still on the training.
I think I would just like to thank everybody for being here today or listening to this very long 2-hour video. I hope I didn't bore you too much with all this all line of code there. And I hope you will be able to extract this code there and use for your application. As I was saying at the start, this is just it's a starting point that try to bridge the gap between machine learning methodologies and between using PoISAR data. You see, the main training is about getting this PoISAR inside machine learning. You will find training on PoISAR on itself. You will find training on machine learning itself. Here I was trying to bridge this gap, and I hope it is useful. You will need to personalize some of the bits to make it more powerful, more robust, less with accuracy, less ridiculously high. But I hope this gives you lets you hit the road running when you want to apply your methodology. And just finally to suggest you to keep on using polarimetric SAR data. There is more missions coming in the future. They will be nicer soon. There will be biomass, and there are many other missions that will acquire also quad polarimetric data. So there is a lot of information there. A lot of research needs to be done, but I think we are getting to better and better products with these things. So thank everybody for this time, and I hope this will be useful for you.
Well, Dr. Marino, thank you so much. This was an excellent presentation and demonstration, and the way that you were able to answer so many of the questions so succinctly and thoroughly is just fantastic. I do want to remind everybody that the question and answer document will be uploaded to the training page by next Tuesday. So please do, if we did not get to your question today, we will address it, we will answer it, and you will be able to get that answer by next week. And also a video of today's presentation and demonstration by Dr. Marino will also be uploaded as a YouTube link to our website by tomorrow, within 24 hours. So as we conclude, I want to thank everybody for joining today. We do hope you will join us on Thursday for part 2 of this webinar series. We have a lot of great material that we're going to be covering over the next 2 parts. So please do join us on Thursday. And as we conclude, I want to thank Dr. Marino one more time for the excellent kicking off this training series. And I also want to acknowledge all of the ARSET team that is working tirelessly in the background to produce this training for you. That's Selwyn Hudson-Odoi, Sarah Cutshall, Natasha Johnson-Griffin, Jonathan O'Brien, Brock Blevins, and Amita Mekta. So thank you to the ARSET team, and we look forward to seeing you all on Thursday.